Okay, for week 6 screencast, I would like to, show my work that I've done, and this includes the PhET simulation charge and fields. I'm just going to go ahead and do it this way because I think this is a fairly useful way to look at work. And so, for the most part, this made sense, and I understood what was going on. And it was also a good way, I think, to understand whether or not the potential was zero in between charges or the field was zero. And so I thought that was an interesting exploration. For example, when you have opposite charges, you would have an electric field in the center, but your potential would be zero. And I thought it was an interesting set of questions to get at the idea of negative versus positive voltage and how you could, go ahead and think about whether or not it's positive or negative work that needs to be done on a charge to move it closer or further from another charge. And so I do have a couple of questions, but I'll get to those here in a minute. It's an interesting pattern, looks like, of potentials around two like charges. And so I went ahead and I took some notes on material. I thought it was interesting to relate force diagrams to the fields and the potentials and the charge that's put in between the two plates. I also worked through worksheet 3, and I struggled a bit with thinking about these equations and trying to understand them. I'm getting closer. I feel like I'll be able to teach this in a much richer way because I will have a much more deeper understanding of these equations and exactly what they mean. And I'll also be able to relate these equations to gravitational fields and forces. And so the kids will have something more to relate to that they've seen before. Vectors and directions and summation of vectors to get at the net force. And this leads me to my questions. And I guess I'll start out with the first question. And the first question is, the idea that when you have two plates that have the same charge, same amount of charge on the positive and the negative plate, it does not change the electric field strength if you move them closer together or further apart. In this case, from the initial to the final, they're getting further apart. The electric field strength is the same for both. And this seems difficult for me to understand. But I guess if we think about the electric field strength as potential divided by displacement, then if you keep the potential the same and you change the displacement, you will change the electric field. But the potential is changing. The potential difference between these plates is changing as they change their distance apart from one another. And so the change in potential, the increase in potential, as well as the increase in displacement result in the same ratio and thus the same electric field strength. And I believe that's a legitimate thought process. It is somewhat interesting and, I don't know, counterintuitive, I guess, for me to think that the electric field strength stays the same no matter the distance between your plates. But you'd have to change the charge in order to change your electric field strength. Yes, that's the moral of that story. Anyway, and another question I had was regarding, let's see, the mapping potential, exploring electric potential with the FET simulation. This problem here, number 14, talks about how my force and energy diagram would change if the sheet to the right were also positively charged. And so if they were both positively charged, both plates would have the same potential. Therefore, there would be zero potential difference. And if there's zero potential difference, and the equation E equals electric field strength equals potential difference divided by displacement, if the potential difference is zero, then that would equal a zero electric field strength. And that would go for anywhere in between those two plates. And so also, since the electric energy is a function of, let's see, electric energy, equation for electric energy. Is Q times, is charge times your potential difference. Since there's no potential difference, there would be no energy stored in the field for this charge, which also seems interesting because there are forces acting on the charge, but the net force would be zero, and so it really results in no effect. So that's an interesting idea. It's also interesting to bring in the energy bar charts. So right here we have energy bar charts, we have force diagrams, and then we also have equations and, just thinking about straight up electrical potentials and fields. So again, very useful to use these techniques, the modeling techniques, in our units, in all our units as we go through them. So that's really a great way, and to give our students a toolkit that can be used to analyze problems across concepts and topics and units.